Section 9.3 is on two dependent samples, or matched pairs. And in order for us to naturally use the methods in this section, we need to have the matched pairs. And the advantage to matched pairs, an example of that, as we have seen in the previous lesson with this, before and after measurements. It reduces extraneous variation, which could occur in two different independent samples, since we're talking about two different people, and the whole point of the independent samples is that they're not paired in some way, so they can introduce extraneous variables and whatnot that might impact the actual study. When designing an experimental planning and observational study, using dependent samples with matched pairs is generally better than using two independent samples, due to the fact of trying to reduce that extra variables, the variation, the looking variables. So this tries to reduce any of those looking variables. Along with other variables that might impact and also try to reduce any other variables that might try to impact the study as well. But anywho, the inference though about the difference from matched pairs, we have the natural requirements. The sample data must be dependent for this, be matched pairs, since that's the whole point of this. But despite that, those matched pairs still need to be a simple random sample. And then either or both of the following is satisfied. The number of pairs of sample data is large, so the sample size for the first sample and the sample size for the second sample both have to be greater than 30. Or the pairs of values have differences that are from a population that has a normal distribution. Again, this uses the t distribution, so this is robust against departures of normality for small samples. If it has no outliers and is not too extreme departure from normality, we could still use this. The test statistic for dependent samples, where the null hypothesis is that the mean of the differences is equal to 0. Our test statistic t is equal to the average difference minus the average of the sample difference, I should probably say, minus the average population difference divided by the standard deviation of the differences divided by the square root of the sample size. Since again, the fact that these are matched pairs, they should have the same sample size. The p-value and critical value or values are computed in SAS, as we'll be doing in a few moments, with degrees of freedom of n-1. Again, they have the same sample size. The confidence interval is that we take the value of d bar, so the sample difference, plus and minus the margin of error e. So that margin of error e is the value of t sub alpha divided by 2 times the sample standard deviation of the differences divided by the square root of the sample size. Again, degree of freedom of n-1. The procedure in order to actually compute these inferences, we first need to verify the sample data consists of dependent samples or matched pairs, and that the requirements are all satisfied. Find the difference d for each pair of sample values. Be consistent. So if you're going to use one way, use the same way the entire time. So such as before minus after, or after minus before. Doesn't particularly matter which one per se, but be consistent the entire time, since the order of this does indeed matter. Find the value of d, the sample differences, the average of the sample differences, so d bar, the mean of those differences, and the standard deviation of those sample differences. For hypothesis tests and confidence intervals, we use the same t-test procedures used for a single population mean. Since the hypothesis test and confidence interval in this section use the same distribution and standard error, they are equivalent in the sense that they result in the same conclusions, which is nice. So, for example, this table down here lists body temperatures of 5 subjects in 8 a.m. and at 12 a.m. The data are matched pairs because each pair of the temperatures is measured in the same person. So we have one person, second, third, fourth, and fifth. Data is set to list 69 of such data for day 2 of the observations, but we are only using 5 of them. So we can easily show the steps for this particular procedure. But using this data down here, with a 5% significance level to test the claim that there is no difference in body temperatures measured at 8 a.m. and at 12 a.m. Now, I should probably note before going through this example, the way that I have this data table coded. I just have the actual data. So I wrote the temperature at 8 a.m. and 12 a.m. as the 2 columns, and then all of those data points inside of here. Note how I did not include the difference, since SAS will do that for us. And quite honestly, there's really no particular real reason to be attempting to put that in there. But I already have this data inside of SAS. Let me just very quickly change this title so we can see it a little bit nicer. Alrighty. So the actual code that we need to use for this, just like in the last section with the 2 population means with independent samples, we're using proc t-test. And the data that we're using here is work.temperature, which is why I just named it. So data is equal to work.temperature. The order we're going to use is the same order as the data. That is, again, pretty standard for these. Alpha is going to equal to be 5%. And it'll be helpful if I typed 5% correctly. 0.05. The test for this, again, we want to look at the differences. We want the plot of this to be normal. I don't believe this is supposed to be an equal sign. Plot, normal. Okay. And now here we are using paired. We use temperature at 8 a.m. So typing it the same exact way it was coded in the Excel file, but we have to use underscores instead of spaces. Times temperature at 12 a.m. And then we're going to run this. So running this, and this gave me an error. Why is that? That gave me an error because I did not put oh, I know what happened. Yep, I know what happened. Okay. I did not type it in correctly. That would be helpful. So let me just move this back over and we can fix that. We don't need these. Nope. We have test is equal to the difference. We need side is equal to 2 for this, since we are looking at if there's any specific difference with these. And we need that the null hypothesis is equal to 0. Well, I mean, we technically don't need that in there, but it is helpful to have that written out as is, since I should probably have written out the hypothesis test before typing all that in. We need to have checked those assumptions, so we know that these are all dependent samples, so these are fine. And we could assume that they're independent. Well, excuse me, assume that they're simple random samples. And based upon this, there are no outliers. And if we attempted to look at a Q-cube normality plot for this, it would work approximately normal. Although again, there's only 5 inside of here, so do bear that in mind. But the actual hypothesis test that we're looking up for this is that the mean, population mean of those differences is supposed to be equal to 0, and the alternative that we want for this is that there is no difference in body temperatures measured at 8 a.m. and 12 a.m. So because of this, we know that the null hypothesis is that there's no difference, that the mean is 0. The alternative would be that there is a difference, so this would be not equal to 0. Which is why we're using a two-tailed test instead of the test here in SAS. But let's run that. And once it takes its time, there's only 5 data points, pair data. So it shouldn't take too long for SAS to actually run that through. Hopefully, anyway. Alrighty. So, before I get to the actual conclusion up here, I should probably note, if we look at the histogram based upon this, this was the 95% confidence interval for this. Do note how that looks all over the place. It's definitely not necessarily exactly normal. We have the paired profiles. Down here's that QQ plot. Excuse me, not QQ plot. This is the scatter plot for that, showing those values. Here's the QQ plot of the differences, which arguably, again, they do not make a nice straight line, as you can imagine, but they are pretty close to that line, except for this point up here. That's the only potentially questionable one. Otherwise, it's kind of close-ish to the line. The actual test itself, it gave us a t-score for this of negative 1.11. And a p-value, when we add up the two tails for this, we get a value of 0.3281. Alright, and we know if I draw out I'll do it up here. If I draw out the normal distribution for this, and a value of negative 1.11, and we have positive 1.11 on the other side here. If we added up these two areas, which is again what we're doing in this two-sided hypothesis test, we would get the p-value of 0.3281. Alright, and because we got that p-value, we can give our conclusion for this. So let's write that out, shall we? So our conclusion for this is at the 5% level of significance. If I could spell, that would be helpful. Significance. we do not have sufficient evidence. And why do we not have sufficient evidence? Because the p-value is 0.3281, and that's a lot higher than 5%. That's what, 32%? 32% is a lot higher than 5%. So at the 5% level of significance, we do not have sufficient evidence to warrant rejection of the null hypothesis that the mean of the differences is 0. And I should probably have noted that this was the population mean, not the sample mean. Population mean of the differences is 0. We do not have sufficient evidence to reject that hypothesis. Where there is no difference in body temperatures measured at 8 a.m. and 12 a.m. Now, using the same data from example 1, we want to construct a 95% confidence interval estimate of the population mean of the differences, which is the mean of the temperature differences. By using a confidence level of 95%, we get a result that could be used for the hypothesis test in example 1, which is indeed true. And, as you can see here on the right, we already have that confidence interval. Since we already have all of those assumptions checked, we don't really need to redo those. Everything else on there is already done. We are given the confidence level right here. So for the 95% confidence level, we have a temperature reading for the lower bound of negative 1.47. And the unit of measurement for this was degrees Fahrenheit. I know it's very strange to see a negative value for that, but that's with regards to these differences. Do keep that in mind. Is less than the population difference. Is less than the upper bound for this was 0.63. Degrees Fahrenheit. Can't forget the units. So, since we have that, we can now give a kind of an explanation of that. Let me just decrease this font size so I have more room. We are 95% confident that the limits of negative 147 negative 1.47. Let me type it like this so I can include that degree symbol. Negative 1.47 degrees Fahrenheit. And you find that degree symbol. Limits of negative 1.47 degrees Fahrenheit and 0.63 degrees Fahrenheit contain the true value of the mean of the differences between body temperature at 8 a.m. and at 12 a.m. Since this includes 0, right, since negative 1.47 and 0.63, between those we do have the value of 0, it is possible that the mean of the differences is equal to 0, where there is no significant difference between the 8 a.m. body temperatures and the 12 a.m. body temperatures. But again, this does have a sample size of 5, so bear that in mind when looking at that conclusion. And then according to the freshman 15, college students typically gain 15 pounds, or 6.8 kilograms, during the freshman year in college. Data set 10, freshman 15, includes results from a study designed to test that common belief. We want to test the claim using a 5% significance level. Due to the way, and I should probably show the data set actually while talking about it, I have it here in SAS already, and that being, let me open it. This is the data set. So do note that this is for each individual person. They weighed them in September and in April to show the either weight gain or weight loss. So because of that, we know that these are dependent samples. And we could assume that we have a simple random sample, even though we technically do not know if this is simple random, due to the fact that this does not really give us an explanation and if it is or if it is not. The sample size of this is 67. That's greater than 30. So we could say that this is approximately normal. Approximately normal. And so based upon that, we're going to call the mean of the population mean here of the differences to be the April weight minus the September weight. Alright. In order to note those, we are saying here, because we're told that the weight gain is 6.8 kilograms, the null hypothesis is that the mean of the differences is supposed to equal to 6.8 kilograms. Do note how this is not 0 this time. The alternative is that the mean of those differences is not equal to 6.8 kilograms. And we want to run this, we want to test the claim at the 5% level of significance. And in order to do this, we're going to look at the confidence interval, although the p-value will certainly give us the same answer. So, because we have this already in SAS, I don't really need to do anything else to actually use it. Let me very quickly make a new program so we could use that particular data sense out of it. And for this, we are going to use, again, the procedure t-test. This data is going to be in temp. Why did that not go on? Underscore temp 0 dot. We are using the freshman 15 data set. So underscore temp 0 period underscore 10 underscore freshman underscore 15. The order of this is still going to be in the data. The alpha of this, we want alpha of 5%. We want the test of this to be the differences. If I could type diff, that'd be helpful. The set that we want is a two-tailed hypothesis test, and the null hypothesis is that we want this equal to 6.8 as opposed to 0. So this is one of the rare times that that's actually needed. And with the way that the data was coded here, we are looking at the September and the April weights. Alright, and we want to do the September weight, the April weight first, and then the September weight. So the way that we need to do this, we're using paired. We want the April weight first, so this will be WT underscore April. So the first variable needs to come first, and this all needs to be capital. The first value that we use for the population, since we wanted it to be April first, that's why April needs to come first in this. Then we have an asterisk, and then the weight for September. Again, based upon the order that we want, which is why we need that in there. And then we're going to hit run. And then it's going to take its sweet daily time to compose those graphs, give us all the information. If we look at the distribution down here of those confidence intervals, note how that looks pretty normal. If you look at the actual scatter plot, that looks pretty centered around that line. And if we look at the quantile plot, do note how that is, I mean, for the most part, going near the line. There's some variation there that might be questionable, though. But by looking at this, though, we are given a t-value here of negative 11.83. That is a very low t-value. The probability is well less than 1%. Well, less than 0.0001. So, very low percentage. But we are specifically going to look at the confidence interval for this, as opposed to writing out the hypothesis. Which, again, this is going to have the same conclusion anyway. The 95% confidence interval for this is going to be the value of 0.2 kilograms. Is less than the population mean of the differences, is less than 2.1 kilograms. Again, based upon what we have here. And now we can write our conclusion for this. And again, let me just change this font size so it fits. We are 95% confident that the limits of 0.2 kilograms and 2.1 kilograms contain the true value of the mean of the difference between the April weight and the September weight. The confidence interval does not contain 6.8 kilograms, since it's way lower than that. Which means that we have sufficient evidence to warrant rejection of the null hypothesis. The weight gain, we could also say that the average weight gain is between 0.2 kilograms and 2.1 kilograms. Or we could say 4 tenths of a pound and 4.6 pounds as well, depending on which way we're referring to that. An alternative method that we could use when the population is not normal and the sample size is less than or equal to 30 is to use the Bootstrap method, which we've looked at before. If the requirements are violated, we can use the Bootstrap procedure for a confidence interval estimate of a parameter. For each pair of data values, we want to find the difference d, and then use the list of differences and apply the Bootstrap method. This uses percentiles to find the confidence interval that can be used for the hypothesis tests. Let me know if you have any questions or concerns. Thank you.